The universality of complexity thresholds. All physical behaviors are bounded by complexity. These thresholds may be subtle or blurred, but sometimes they appear as sharp transitions where entirely new behaviors emerge. Quantum systems show this principle clearly. Small systems exhibit interference and superposition. But when interacting degrees of freedom cross a threshold, decoherence dominates and the system reorganizes into classical behavior. Gravitational dynamics also illustrate this principle. In planetary systems, gravity follows Newtonian mechanics and general relativity with high precision. But in galaxies, stars rotate with nearly constant speed at large radii, a new gravitational behavior not seen in simpler systems. Phase transitions give some of the clearest demonstrations. Water abruptly becomes vapor at its boiling point. Magnetization disappears above the Curie temperature. Superconductivity emerges below a critical threshold. Networks suddenly percolate into global clusters once connectivity is high enough. Large language models provide another example. Small models behave like statistical pattern matchers. But once parameter count, data scale, and training complexity cross certain thresholds, emergent capabilities appear, reasoning, coding, and abstraction, that were absent in smaller versions. These examples show that behaviors themselves are bounded by complexity thresholds. Once critical limits are crossed, behavior reorganizes into something qualitatively new, and no simple extrapolation from the previous regime will suffice. Algorithmic information theory provides a mathematical codification of this principle. Kolmogorov, Solomonoff, and Chaitin demonstrated that complexity generates irreducibility. Once systems cross certain thresholds, no algorithmic compression can fully predict their behavior. Because physical behaviors are bounded by complexity, the theories that describe them are also bounded. Problems arise when we forget this and apply a theory outside the complexity domain, where it was originally calibrated and empirically validated. Quantum mechanics works beautifully for quantum systems. But when extended uncritically to macroscopic complexity, paradoxes appear, such as Schrödinger's cat or the free will theorem. These paradoxes are not properties of reality, but artifacts of applying a theory beyond its limits. General relativity is calibrated in relatively simple gravitational systems, such as planetary orbits and binary pulsars. But when extrapolated to galaxies or the entire cosmos, tensions appear. The constructs of dark matter and dark energy highlight the boundedness of the theory, not the failure of reality. The deeper lesson is clear. Behaviors are bounded by complexity thresholds. Theories inherit those bounds. Paradoxes and tensions in science often arise not from nature itself, but from our insistence on pushing theories into regimes where complexity makes them inapplicable.